evening and welcome to Tinkering with Edkelar. Today on the stage I have a Nabu PC, or NPC for short. Like many others, I found out about this piece of computing history through a video on Adrian's Digital Basement and immediately had to get one myself, so that I could be at the peak of the wave of exploring it. But since I live in Central Europe, in the middle of nowhere, rather than anywhere in the US, the hype was already somewhat dying down before I even received the box. And just tagging along is no fun at all. So much for cutting edge. Let down by geography and postal services yet again. But I still wanted to scratch my reverse engineering itch and try to do all the things that went through my head immediately after watching that video. So I decided to completely ignore almost everything about the device and get started from scratch. I only used the schematic that I found on Google, so I didn't have to trace out the PCB myself. For those who have not yet heard of it, this unit was intended to go with a matching cable TV modem to provide mostly download-only content to the user, sort of like a teletext viewer with a bit more features. It is referred to as HCC, or Home Cable Computer, with the modem being the HCCA, Home Cable Computer Adapter. The box arrived as advertised. New, old and slightly moldy stock. That means that this unboxing is sort of special, since it is a very rare chance to unpack a retro device that has last seen the light of day in the factory. The box contains an owner's manual, the keyboard, a smaller box and the main system unit. Contained inside the sub-box is the keyboard cable and a short length of RF cable. The main unit has connectors for RF in-out, audio and video out, the keyboard, a printer and the adapter, i.e. the cable modem. On the front there's a power switch, some status LEDs and a reset button. Let's take it apart. Even if I weren't to do the usual recapping, I would still need to slightly mod it. The switch mode power supply is 110 volts only. The main board reveals an assortment of chips, as expected, and 4 expansion slot headers. A Z80 CPU clocked in at about 3.5 MHz provides the core. A TMS9918A video processor creates an NTSC video signal, and an AY38910 sound chip creates the beeps, boops and bleeps. 2 other chips take care of the keyboard and modem communication, the rest is RAM, ROM and some glue logic. There is also a rather curious power resistor. The free-flowing placement suggests some heat buildup. Here's a quick side note on that resistor. The keyboard is officially powered by unregulated 9V DC, which is not really true. It is powered by 12 volts across this power resistor. That makes it more of a current limiting measure. This might lead to just about 9V at the connector, but it is nowhere near promised. It might be a good idea to replace this with a DC to DC converter brick eventually to avoid that space heater. The keyboard has a built-in 5V regulator anyhow, so anything above the dropout voltage is fine. The connection between the main PCB and the power supply can be summed up as messy. There are some power rails connected in transit for whatever reason. More fun for the electrons. Removing the power supply board. The ground lug just pulled out. As in, the lug pulled out of the PCB. If you have one, better check that spade connector. The fan at the rear is an AC 110 volt one. I need to replace that too. Oh, the fan blades actually scrape over the outer shell. Yikes! The keyboard contains another PCB with quite a large chip count. Interesting. It is almost a computer on its own. The keyboard contains two joystick ports on the back. They seem to be compatible with the Atari and C64 connectors, but they don't have the pedal inputs connected. Now to the usual recapping. Some of the caps are rated 100 volts, which is a bit high. I'm replacing them with what I have at hand. Again, just as a precaution, because electrolytics are wet. There is no visible damage and these predate the capacitor plague. I just feel better with newer ones. Putting the keyboard back together. No cleaning required for this one. Followed by the main unit. The power cord was wrapped up with a rubber band, which has since turned into some splintered and rather brittle residue on the cable. Meh. For the new power supply, I'm drilling a few mounting holes to bolt it down with a few standoffs. I also put in a suitable 12-volt fan. A better replacement later on. This one is a leftover from another project and sadly had the mounting holes clipped off for that. So I needed some shims to hold it in place. To avoid waiting for a PCB, I cobbled together an adapter for the original connectors to the power supply. Eventually, that adapter shall be replaced with a custom PCB one, but for now, this improvised one shall do. The mains connector actually does fit the new one. And now, the big moment. Let's see if it turns on. I have this tiny portable LCD TV that makes for a good test screen. Picture! Now, here's where we dig deep into the coding side of things, so brace yourself. While I had the mainboard out, I also took an image of the ROM content and started to disassemble it. At first, some of the disassembled code didn't make much sense. But as I started to read, interpret and comment on the boot ROM code, it became clear that the disassembler also disassembled some data blocks. Whoopsie! The data isn't all in the end as I expected, but also right in the middle. Once you separate these parts out, it makes much more sense. Step after step it became clear what each block does, replacing the generated hex labels with more descriptive ones, one after the other. At a high level, the boot process is as follows. Set up the ROM execution environment, initialize the support chips, and in case of a cold boot, perform a series of hardware checks. Then initialize the cable modem and prompt the user for the channel code if the modem wants it. The last step is to load the actual OS from the modem and pass execution to that. While the I/O devices are all connected with the interrupt system, the bootloader uses polling to wait for the required conditions instead. I think this is to avoid any nonlinear code paths in the ROM code. Now back to the hardware side. I want to make a modem replacement device that can be used with the stock ROM and yet provide more functionality than the original system had. I did set up a high-level spec sheet in a GitHub repo, so if you're interested in following along, link in the description. To connect the two devices, we need a 5-volt driven symmetrical serial line. That is essentially the same as any common serial port, but with 2 lines per direction for added resiliency against noise. It is formally known as a TIA422B apparently. as luck would have it, the driver ICs are still around. So I connect the required 5-pin DIN plug to the receiver IC and hook that up to the second serial port of an Arduino Mega. That way I can write a sketch that reads from one port and prints diagnostic data on the primary one. It took a bit to make all the connections, but eventually I could read and write data just fine. An important consideration, however, there is no flow control. The Arduino can send bytes much faster than the Nabu can read them, especially in polling mode during boot. Maybe the interrupt-driven read is faster, but I have doubts. So, while the line speed is at 111,860 baud, there has to be a bit of a delay between bytes. To test my idea of running code on the system, I wrote a simple assembler program. Basically a Hello World program. I added the checksum to the binary block and sent it over to the Nabu. And after quite a bit of very low-level debugging, it worked! A bit of testing and some debugging later, I have successfully coded what I consider the beginning of an operating system or kernel. I can use interrupts to send and receive data over the modem as well as the keyboard, and even wrote a simple real-time clock based on the video interrupt. So, where do we go from here? My idea is to write a simple kernel or OS for the Nabu that works in conjunction with my planned modem. At its core, it should provide access to a network, HTTP based, and allow people to load programs from there, use virtual storage space to save stuff, or even connect two Nabus together for a live game. I still need to do some tweaking and final testing on the hardware design before I commission a custom PCB, but I'm optimistic. So let's see what this baby can do when connected to an appropriate network. I hope you liked this episode. See you next time! For the new power supply, I'm drilling a few mountain holes. Yay, mountain holes. It's called caves. Nice. Yay.